television programs.
Hello, teacher. Hello, students. Welcome to today's lesson on nuclear energy. In our last lesson, we reviewed nuclear binding energy, and you learned that binding energy is found by calculating the difference between the mass of the nucleus and the sum of the masses of protons and neutrons that make up the nucleus. Today, we will look more closely at the relationship between mass and energy. Are you ready, students? Let us begin. One of the most important equations in physics is E equals m times c squared, where E is energy, m is mass, and c is the speed of light, 3 times 10 to the 8th power meters per second. This equation belongs to Einstein's theory that a change in energy will be associated with a change in mass. Let us examine how this applies to our study of nuclear energy. Any nuclear reaction that increases the binding energy per nucleon will give out energy. Based on Einstein's theory, we know that a change in energy will be reflected by a change in mass. In fact, if we add up the mass of the protons and neutrons in a nucleus and compare this sum to the mass of the nucleus itself, we find that there is a difference. This difference is called the mass deficit. When the nucleons are grouped together to form a nucleus, they lose a small amount of mass. This mass deficit is released according to the equation E equals mc squared, which gives us the equation binding energy equals the mass deficit times c squared. For systems with low binding energies, this difference in mass may be fractionally small. But for the systems with high binding energies, the missing mass may be an easily measurable fraction. When calculating the binding energy, we often use the notation atomic mass units for the measurement of the masses of subatomic particles. Students, please copy down these measurements for protons, neutrons, and electrons. You will need these for the activity. Using these measurements, please find the mass deficit for a carbon-12 nucleus. A carbon-12 nucleus has 6 protons and 6 neutrons. Please note, students, to find the measured nucleus mass or isotope mass, first calculate the electron mass and subtract this number from the atomic mass. Please go ahead with the activity.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. How did you do? First, to calculate the electron mass, we multiply 6 times 0.000548558. This number subtracted from the atomic mass 12 gives us 11.9670852. This is our isotope mass. Next, we find the nucleonic mass. We have 6 protons at 1.007276 atomic mass units each, which gives us 6.04365 AMU. We have 6 neutrons at 1.008665 each, which gives us 6.051999 AMU. If we add these together, we get 12.095646 atomic mass unit. When we subtract the isotope mass from the nucleonic mass, we get 0.0989374 atomic mass units. Therefore, the mass deficit of carbon-12 is 0.0989374. We can see that our mass number 12 does not equal the isotope mass, nor does it equal the mass of separate nucleons. Excellent work, students. Now that we have worked through the activity together, I am confident that you understand how to calculate mass deficit. If you had any difficulty, please ask teacher to look over your work after the lesson. To calculate the binding energy, we could use the equation E equals mc squared. However, to make things simpler, there is a conversion factor that converts mass into energy in units of mega-electron volts, or MeV. Multiplying an atomic mass unit measurement by 931.5 will give us an energy equivalent in mega-electron volts. Using this conversion factor, students, please calculate the binding energy of carbon-12.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. I am sure that you found that problem quite easy. We simply take our mass deficit measurement of 0.0989374 atomic mass units and multiply it by the conversion factor 931.5. The binding energy of carbon-12 is 92.1602622 mega electron volts. Great work, students. As you have just seen, whenever there is a gain in mass, there is a gain of energy. Conversely, a loss in mass will result in a loss of energy. In nuclear reactions, the energy that is lost as binding energy is emitted in the form of electromagnetic waves such as gamma radiation or in the form of heat. In our next lesson, you will learn more about nuclear reactions such as fission and fusion. You will discover exactly what happens to the binding energies when these reactions take place. Until next time, thank you, teacher. Thank you, students.